Just to let you know that we are going to record the meeting. Obviously, if you have an issue with that, then I would ask you to dial off now. And I think these meetings are going to be posted on the YouTube channel. Is that right? Hopefully. Good. Okay. Gert, do you want to share your screen with us and get your slides ready?
There we are.
Great. Good. I can see that. That's great. Are you ready to start?
I am ready, yeah.
Excellent. Okay, well then, without further ado, let me introduce today's colloquium speaker is Gert Aerts from Swansea University. And it's great to have him here, unfortunately only virtually. I hope we'll see him in person visiting Dublin soon. But in the meantime, I'm looking forward to hearing his online presentation on machine learning for lattice field theory and back. Okay, Gert, over to you.
Yeah, thanks, Mike. Yeah, thanks a lot for the invitation. So this talk is on a relatively new topic for me, I would say. So machine learning for lattice field theory. It's mostly done, or actually completely done, in collaboration with Dimitris Bartis and Biagio Lucchini. So Biagio is a colleague of mine in Swansea, and Dimitris is a PhD student on the Europlex network, which is also at TCD, actually, this network. And then I'm also at TCT Star. So I know people have a background. Some people work on lattice in the audience. Some people work on maybe more formal quantum field theory aspects. But I think the topic is interesting for everyone because there are some new links with quantum field theory that you may not be aware of. And in fact, some colleagues, not in Swansea, but colleagues elsewhere who used to work, say, on, let's call it string theory or formal field theory, have moved in this area of machine learning as well. So there's a lot of things that are quite new and open and accessible to people who are interested. So my focus will be a little bit on my own background, which is lattice field theory, finite temperature field theory, say, phase transitions. And in the second part of the talk, we'll then look at some kind of new developments which are more exploratory. As I said here, this topic has been rising rapidly, I would say, in the past 4 years or so. And there's one reference which I'll point out in just a minute, which is kind of set up a whole slew of papers in the area of phase transitions. But it's still very early days in a way, so I quite like this because I like to work on kind of new things where you don't have to have per mil precision in numerical calculation, but where you can get away with, anything goes, so to say. But there are some new clear directions emerging, and we put a paper out just last month, really, on applications of machine learning to lattice quantum field theory as part of the SNOWMAS exercise, which is the kind of the forward look in the United States. So it was very pleasurable for Biagio and myself to work with all these colleagues who are mostly around MIT, say, to see where this area is going. So in this talk, I'll have some topics to discuss. Obviously, they're very much biased by what we worked on in Swansea. And so there are 4 main topics. The first one on classification of phase transitions is definitely not ours. It's essentially now a classic application of machine learning in this field. So I'll report a little bit about what we could add in this area, and then extend it a little bit by something known as transfer learning. Again, transfer learning is a widely used concept in machine learning. And then the next 2 topics is, I would think they are kind of new ideas, new concepts, new applications. So these are more coming directly from our side. And there's a lot of things to explore here, especially in the last area. For interest for people looking outside of phase transitions or lattice field theories, just as a kind of a new framework to think about machine learning and field theory, quantum field theory, and what they may have in common or not. Everything I say here is based on the following papers. So these have all been done together with Dimitris and Biagio, and the last one also with Francesco Lorenzo in Parma. And so here it starts with phase transitions. And then we move to this quantum field theoretical machine learning and the inverse renormalization group. So let's start with the first topic. First topic is this classification of phases of matter. And this started with this paper from 2017 by Karaski and Melko. As I said, by now it's a classic topic. This paper has over 1,000 citations in a very short amount of time. Basically, because it's quite easy to do something in this area. You just take a model which you know, and you apply this kind of machinery. And because it's fairly new, it's relatively easy to publish. But I'd like to say that we added some new things here which were not done yet, so to speak. So let's start at very elementary. Let's take the Ising model. We all know the Ising model. There are two phases. It can be in the cold phase or the hot phase, or the ordered phase or the disordered phase. And numerically, of course, it's very easy to distinguish what is the ordered phase, the big clusters of spins all pointing in the same direction, and the disordered phase looks pretty random. But to say in what phase this particular system is in the middle requires a little bit more work. Of course, what we do numerically is you compute the order parameter with the symmetrization, and then you should in principle take the infinite volume limit to see whether the order parameter goes to 0 or not. So we know how to do it. But the question is whether we can say something about this problem using machine learning. Let me go to this slide first. So why would machine learning be able to say something? Well, machine learning is used, across many areas: social media, Amazon, whatever you can think of. And basically, what it does is pattern finding. And so the way you do this in supervised learning is to say, okay, we have some configurations now, which are either deep in the ordered phase or deep in the disordered phase, so at very low temperature, at very high temperature, and we want to train a network to predict in what phase the configurations are, and then we give it a new configuration, an unseen configuration, and it will look at the patterns in that unseen configuration and give a probability whether it's in the ordered or the disordered phase. And so that's the idea why machine learning might be useful here. You have a configuration, you put it through a neural network. I will not give any details on what these layers mean here. This is a so-called convolutional neural network with several layers. So it's an example of deep learning. But what training the network means, or training the algorithm means, is that the parameters, which are essentially weights and biases living on these layers, that these are adjusted to make the correct classification. And training the network basically says, I know the outcome, I know the output, because I've labeled my set of configurations, and I'm trying to reproduce this output as well as I can by adjusting the weights and the biases in these layers. So this is essentially, you could say it's a fitting procedure, but with many degrees of freedom, and in this case with a binary classification, ordered or disordered. After the network is trained, then you give it a new configuration, unseen configuration, you repeat the same parameters within these layers, and a probability will then come out that this particular configuration is either the ordered phase or the disordered phase. This is how, this is the kind of the paradigm of machine learning with deep neural networks. You do not exactly know what these weights and biases mean within these different layers, but the prediction that comes out is, pretty spot on, so to say. So this has been used in this first paper here, and we want to make it a bit more quantitative now. And to make it quantitative, we have to talk about critical exponents, because phase transitions are universal features of phase transitions. And what we really want to know is the coupling, which is the parameter where the phase transition takes place, and then the critical exponents will tell you how certain quantities diverge when you approach this phase transition. So this is a one-slide overview of this, the Ising model. This is the standard Hamiltonian, or energy is just nearest neighbor interaction. Every spin can be either up or down. There's one parameter here, beta, like the inverse temperature or the coupling. The critical coupling denotes the transition. And then once you approach this transition, the correlation length in the system, which tells you about the correlation, diverges, and the magnetic susceptibility diverges as well, and they diverge in a very specific way determined by the universality class of the phase transition. And so what we want to do in this particular exercise now is reproduce these critical exponents and see what kind of precision we can get just using machine learning, so not using knowledge we already have, say. So the game here is basically not to say, oh, we know this, we know the universality class, we know what the order parameter is, it's obviously the magnetization, we know the susceptibility, which is the fluctuations of the magnetization. We want to do something which purely relies on machine learning quantities. And so this is what we do here. So again, this neural network will give an output, which is a probability, which lies between 0 and 1, to be in the ordered phase or the disordered phase, or this is symmetric or broken phase. And so what is shown here is the expectation value to be in the broken phase. And so at low beta, you're in the ordered phase or the symmetric phase. At high beta, you're in the broken phase. And on a finite system, this is not a proper phase transition. This is a kind of a crossover. You only get a phase transition in the infinite volume limit. And so you smoothly interpolate from the broken phase to the symmetric phase. Now, what is shown in this plot here, this is the output from the neural network. And so you have to train a neural network. You have to give it labeled configurations where you say the one on the left is clearly in the ordered phase, the one on the right is clearly in the disordered phase. And this training is done at values of the coupling constant, which is far away from the critical coupling. So the critical coupling is about 0.44. And so the training is done at less than 0.41 and more than 0.47. So it's off the scale on both sides. So the training is done really, really very far away from the critical region, where it's clear that you're in the ordered or the disordered phase. And then the rest is a prediction. Now, there are symbols here and lines. So the symbols are the output from this convolutional neural network directly. So we've done a Monte Carlo simulation, created configurations of spins of an Ising model, and give this set of configurations at a given beta value to the convolutional neural network. And this is the probability that the system is in the broken phase. So that's a prediction. On top of that, okay, and I'll come to the black diamond in a minute. And so what you can see already here is that this probability essentially behaves as an approximate order parameter. It's 0 in one, 0 in the left phase, 1 in the right phase, and it interpolates smoothly between them. It behaves in an order parameter also in the sense of finite size scaling. If you increase the size of the system, so this is the two-dimensional Ising model, this transition becomes sharper, as you expect, and it also slightly moves with beta, which is what you expect from the finite size scaling. Now, this what I just described is very well known. This was already in this first paper, and this has been reproduced for many different models and so on and so forth. So what is new here? And so we, in this paper up there, we try to add something new, namely that this probability that comes out of the neural network actually can be seen as an observable in a statistical system. Maybe a slightly weird observable, but it has all the features of how we compute observables, say in numerical field theory. Namely, we have a set of configurations. We do something with this configuration. We compute something on this set and then take a statistical average. And the output will be some expectation value, which in this case is a number between 0 and 1. Now, this is exactly how you would compute, say, the magnetization or the susceptibility or the specific heat, say, numerically in a lattice simulation or a simulation of a spin model. You take some observable, you take some quantity, you average over your set of configurations, and you get some expectation value. And so this probability here can be seen as a expectation value over this ensemble of configurations, and therefore it's essentially Boltzmann weighted with configurations that are you know, produced by Monte Carlo sampling according to the Boltzmann rate. So that's the notion here, that the output of the neural network can be seen as a statistical quantity in a physical system. Once you accept that, then you realize that actually, then we can use standard numerical methods or standard statistical methods that we know very well in statistical theory. And for instance, we can do histogram reweighting. So histogram reweighting is a technique where you do simulation at one value of the coupling constant, but you would like to know values of observables at around for different values of the coupling constant in the neighborhood. And you can do this by reweighting, which is essentially a correction in this Boltzmann weight. So the simulation is done at a value beta sub 0, and then you can extrapolate to different values of beta by putting in this correction factor, which takes care of the fact that the Boltzmann weight is slightly different at values of beta, which are different than beta 0. And that's exactly what is done here. So the black diamond is obtained by direct simulations at this value of beta of about 0.438 or so. But then using histogram reweighting, this entire line is produced just by reweighting in beta, so single parameter reweighting. And this means that from one simulation in the critical region, we can extrapolate or reweight all the way to the ordered and the disordered phase, which is exactly what you normally do in histogram reweighting. Except, of course, that is the quantity here is this output from the neural network. It's not the magnetization directly, so it's this neural network output. And the good thing, of course, is that I told you these open diamonds were the results from direct output from the neural network, and the line luckily goes through these points here. So that's the fact that we can rely that this histogram reweighting is working. We can do a direct neural network calculation at discrete points, and this matches up with the continuous line from histogram reweighting. So that's the first kind of new feature here. So it's we interpret the neural network output as a physical observable. Now, once you accept this, you can continue your analysis and do standard finite size scaling, not on, say, the magnetization, but instead on these outputs of the neural network. So this is a statistical quantity here, this probability. It's computed by averaging over configurations. And so we can also look at fluctuations of this quantity. And that's what you call the susceptibility. So what's plotted here is the susceptibility of this neural network output, not of the magnetization, say. And this susceptibility behaves as you expect, namely on larger volumes, it starts to diverge. And there's also a slight dependence on the beta value, where the maximum is depends on the system size. So it slightly moves to the right here. Now this is, say, relatively standard finite size scaling, so we can put the critical beta as a function of the volume or 1 over volume on a line, and indeed these points nicely line up, and we can extrapolate to the infinite volume limit to have a prediction for the critical coupling in the infinite volume. And that's what's given here in the table. The two-dimensional Ising model is exactly solvable. So there are exact numbers here for the critical coupling and for the critical exponents, mu and gamma over nu. But from this extrapolation and the infinite volume limit of these curves, we can compute these quantities separately. And you see that they agree with the theoretical predictions. Now, just to say it one more time, the point here is that the top line here has been computed using only properties or observables from the neural network, namely the probability to be in the broken or the symmetric phase, and then fluctuations of this probability once it's averaged over configurations of the ensemble. So we didn't have to use knowledge of the order parameter or the symmetry class, etc., etc. It's purely based on neural network observables. So that's the first part here. So let me briefly say, the proposal was to identify neural network outputs as observables in statistical physics. Once you accept that, then you can use all the tricks, you know, from statistical physics, numerical statistical physics, say. And so this is histogram reweighting as one example. And then using finite size scaling on neural network quantities alone, you can indeed get the critical properties in agreement with the expectations, so to speak. So that's an interesting synergy between machine learning on the one hand and statistical mechanics, statistical physics on the other hand. I'll pause for questions. I don't see any. So let's go to the second topic then. So this is interesting. This was on the Ising model. Of course, the Ising model is very well known. But can we use the knowledge learned on the Ising model in other models now? And in particular, we had trained this convolutional neural network, and there are features in there. Obviously, it learned features on whether the Ising model is in the symmetric phase or the broken phase. And so you can ask yourself the question whether these features are sufficiently universal to also predict phase transitions in other systems. And this is something called transfer learning. Again, this notion of transfer learning has a long history in machine learning. In this context, it works as follows. Suppose we have a neural network trained in one model where it's able to distinguish two different phases. What if we give the same neural network to another model, like a POTS model, or even a model with continuous degrees of freedom, like the 5⁴ theory? Will this network still be able to say?
Well, sorry to interrupt. There's a late question in the chat from Michael Mitchell saying, sorry for the late question. Why train on values of beta far away from the region you're interested in?
Yeah. No, indeed. So the idea is that you don't want to your bias. You don't want to say, well, actually, I know that the transition is around 0.44, so I'm going to train it here. Because these are the configurations which are difficult to label. So in this case, of course, we know where the transition is, so we know where we are. But even so, suppose we would not know the transition, just by eye, you would be able to say that this, the left here is in the ordered phase, the right was in disordered phase. But we wouldn't know about the one in the middle. So we want to essentially keep it open for anything in the middle where we're not quite sure, and let that be predicted by the network, and only use labeled data which is sufficiently far away from the region of interest. Yeah. So it's not to bias the outcome, and especially in cases where we do not know what the outcome is. So this is transfer learning. We use exactly the same neural network, but now we give it, so it's been trained on the Ising model, but then we also give it configurations in the POTS model, or in a theory which, so the POTS model has discrete spins as well. 5⁴ has continuous degrees of freedom, and we then still are looking for a prediction order or disorder. So how does this work? So this is for the POTS model. So again, this is this probability that lies between 0 and 1. POTS model is a spin degree of freedom which has, say, 3 states, 4 states, 5 states, etc. So the 2-stage POTS model is essentially the Ising model. And again, the transition is known analytically. The critical coupling is given down here, and given by these dashed lines. And so we do the same exercise. We train on the Ising model, then provide data from the POTS model, and then use histogram reweighting to get continuous lines. And as you can see, that the transition does take place at where we expect it to take place. So the knowledge gained from the Ising model is sufficient to learn about this. It is actually interesting because the Ising model has a second order transition, and the POTS model only has a second order transition for Q equals 3 and 4, but it becomes first order for 5, 6, and 7. So even the change in the order of the phase transition is in a way irrelevant to be able to see this transition takes place. So it learned features which are, say, universal enough that it's robust against changes in the order of the phase transition. I'll say a little bit about
practical question here. I mean, so now you've obviously got different degrees of, the input image, if you like, is in the Ising models, it's 0, plus or minus. Yeah. And now in the Q-state, 5-state POTS model, you've got numbers from 1 to 5. So, I mean, how do you must have to sort of pre-process your images.
So they are, it doesn't have to be, so they don't have to be discrete indeed, but in this case, they are mapped between -1 and 1, say. And the ones that are in the middle are left. So the 5 states, say, are mapped to -1, -0.5, 0, half, and 1. Okay, so it's the same range, but not exactly the same values. Say, yeah. That question becomes even more important now when we apply it to a continuous field theory. And there it turns out that not much has to, I have to actually look at the paper, what exactly is done, but the state of field variable also roughly has values between -1 and 1, say. But it's a continuous value, so there are configurations where the phi field has large values. But it's remarkably robust indeed, yeah. But indeed, so the input layer in the convolutional neural network can take any value, so to speak. It's not a discrete input layer. Now, this phi to the 4th theory is more interesting for 2 reasons. One, it's a continuous field theory, but also the answers are not known analytically. So it's known in which universality class it lies. It's the 2D Ising model. So we know the critical exponents, but we do not know the critical parameters. So what is done here is that, again, we use the neural network trained on the Ising model, then work with fixed lambda, fixed coupling constant, and vary the mass parameter. And using the Ising model neural network, the prediction is then that for these large negative values of mu squared, the model is in the symmetry broken phase, and for these smaller values, it's in the symmetric phase. So what this tells us is that we can identify the region where the phase is clear, where it's symmetrical broken. So we can then retrain the neural network in these intervals to the left of -1 and to the right of -0.9, and then repeat a finite size scaling as before. So the parameter we're interested in here is mu squared, so the critical mass parameter, so to speak, which triggered the transition like this one from broken to unbroken potential essentially. And so this is a finite volume data, and then you can extrapolate. So this critical coupling there's no analytical answer for it, but it agrees with other methods. And actually there's a paper by David Shake who looked at this for his master thesis or something. So for those of you who know David. So that's one thing. And then the critical exponents are actually in agreement with what you expect from the universality class, so 1 and 7/8. You have to retrain the neural network. Initially, we didn't, so we just used the Ising network completely. Then, of course, you get an output, but it's not very precise, basically. So the proposal made here is essentially that you use a network trained on a well-understood model to identify the phases, and then you retrain it in regions where it's clear which phase you're in to gain the precision that you're after with so many digits. A little bit under the hood then. So how does this work? Well, this neural network has all these neurons, which are essentially just numbers living on a layer, 2-dimensional layer. And so this, I'm looking here at, if I go back this plot, and I'm looking at the values on this layer. And basically what you see in that all these models, the 2D Ising model, the POTS model with 3 and 5, or the 5 to the 4 model, the 2 phases are clearly encoded in these values of the weights or the neurons in this layer. So in the ordered phase, they're relatively small and they're present almost everywhere. And in the disordered phase, they're quite large and only a few neurons are switched on, so to speak. And that kind of explains, at least not in a hands-on way, explains why these features are the same across these different theories, because the different theories show up in the ordered or the disordered phase in the same way in terms of which neurons are switched on. And so that's why it's possible. So brief summary on transfer learning then. So we can use a simple model to study a complicated model. That's the idea. Once you've determined that there is a transition, you know which region of parameter space would be interesting. And so you can then look at that region more precisely, use reweighting and really find the transition, and use the same finite size scaling as before. So again, I'll stop for some questions if there are any. I have a kind of a lot of topics, so it's like a whole course in machine learning done in 60 minutes. I would have been, I would decouple by now in the talk, but I hope you won't. So the next topic is slightly different. So the first two, as I said, the detection of phase transitions and also using transfer learning, to be honest, are quite well known and have been done quite a bit. And the next two topics are kind of new, I would say. They haven't been done. It's really Dimitrios, our student, who came up with all of this. So it's really his strength here. And so this talking about something called the inverse renormalization group. And this is something that you know doesn't exist, so to speak. And so what is meant? Now, the standard renormalization group is obtained in the statistical physics sense by integrating out degrees of freedom. So you can call it coarse graining or blocking. And you go to systems where you have less and less degree of freedom because you represent, say, a certain area or space volume in your configuration by a single number. So you're integrating out degrees of freedom. And the prime example here is Kadanoff block spinning in the Ising model. So here I have a 4x4, say, Ising model, a configuration. And if I integrate out spins, I replace, say, 4 spins in this square here by just 1 spin here. I use something like called the majority rule. In this case, I have 3 black spins and only 1 white one. So this one becomes black. Here is the opposite, so it becomes white. And if it happens to be that 2 spins have the same, that are as many spins up and down, I can flip a coin to determine that, in this case, 2-2 happens to become white, and this is 2-2 happens to be white as well. So this is block spinning. This is something that's very well known since the 60s, and then with Wilson formulated as a proper, renormalization group. And from this, you can extract critical properties, and it generates a flow in your coupling space, essentially. Now, the downside is, I mean, the renormalization group is, of course, very much celebrated. So I don't want to be negative about the renormalization group, but you can see a practical problem. Namely, if you do this numerically in a numerical simulation, you are integrating out degrees of freedom. And so if you're doing this blocking procedure repeatedly, you essentially run out of degrees of freedom, fairly quickly. Because with every step, you halve the number of degrees of freedom. So this L here is actually more like N, the number of lattice points. And so here we have a 4x4 lattice. After one step, we have a 2x2 lattice. There will be one more step left where we have 1 point only. So if you want to do this blocking type renormalization group multiple times, you have to start actually with a very large system to be able to do this. But of course, it's difficult to have large systems, especially when you're close to a phase transition, because of critical slowing down. That's one of the issues in numerical simulations, that it's more and more difficult to generate configurations when you're probing critical dynamics. So the question is, what if we could invert the renormalization group? So what does it mean really to invert the renormalization group? Essentially, you want to fill in the details. So you have a coarse-grained configuration here, and this can come from an original configuration. Now, we do not know. I mean, there are many configurations on the left, which, if you would do a block spin transformation, will give you the configuration on the right. So it's not unique. It's not uniquely determined. But nevertheless, you can think about this in this way. Can we find, very likely or probable inverted renormalization group steps, which would allow you to fill in the details and undo the coarse graining? Now, the benefits will be very clear because, well, first, it creates an inverse flow in parameter space. So we actually still probe the critical dynamics. It actually brings you closer to the critical point. But moreover, it can be applied an arbitrary number of steps, because you're not losing degrees of freedom, you're adding degrees of freedom. And in fact, you make your system larger and larger. And in doing that, then you actually can create a large system very close to criticality. And so you evade critical slowing down in this way. So this idea is not new, actually. It was proposed for the Ising model in this paper by Swansea and collaborators, inverse Monte Carlo organization group transformations for critical phenomena. But it's never been done for continuous field theories. So here I want to now show you that with kind of machine learning techniques, you can do this for a continuous field theory like 5^4. So what is the idea? Well, we have to come up with an inverse transformation. Suppose we know how to block spin or coarse grain. We want to undo it, and we want to learn what the inverse transformation is. Now, new degrees of freedom have to be introduced. It's not uniquely fixed, but we can kind of, statistically find an inversion that works. So the machine learning language here is called transposed convolutions, and this creates a fine-grained configuration, basically. And the way it works is as follows. I have here say a 16 by 16 lattice in a theory. I then do a renormalization group, which reduces it to an 8 by 8 lattice. And then I want to invert it by doing some convolution, which makes it again 16 by 16. And this step here, I learn by comparing the original configuration with the output configuration. And I simply want to minimize the difference between these two configurations. So this step here has a number of free parameters, like everything in machine learning has. And by looking at the square difference between these configurations, I want to tune these parameters. It's called transposed convolutions. It's very much how a convolutional neural network works. In a convolutional neural network, you take an image and you have a filter that takes this data and replaces it by some kind of average data. Here we do essentially the inverse. We have some input and say this one block here, one degree of freedom is replaced by 3 by 3 block. So it's an inverse convolution, so to say. Now there's a lot of free parameters here, which are determined by minimizing the difference. It's, you can expert on machine learning like Dimitrios is to implement this in Keras library, and there's all kind of fancy stuff which I'm not an expert on, but I guess the point is that it works, so that's the important message. Now what's really interesting, of course, is that it's a local transformation. So you take part of your configuration space or your configuration locally, and you apply this transformation. It doesn't require any global knowledge. So because you can do it locally, it means that you can keep on doing this. So I can go, indeed, like in this picture here, I can start with, say, 8 by 8, and then do a step, go to 16 by 16, 32 by 32, and I can keep going because I'm only locally enlarging the system by this transposed convolution. So I can do this repeatedly. And in this way, you completely evade critical slowing down because you just have to generate a bunch of configurations on a relatively small system, and then just do this iterated over. It also generates a flow in parameter space. You can actually show that it's exactly the inverse flow that the standard renormalization group creates. And of course, importantly, there's an invariance at the critical point, which means that you can look for intersections of lines to locate where the critical point actually lies. So we've done this in a 5^4 theory. So this is a continuous theory, which is why it is new. And basically, this picture is a little bit hard to understand, but what you should look at is we're increasing the system size here using this inverse renormalization group step, 64, 128, 256, 512, and the fact that these curves zoom in, and so the intersection gets more and more focused, that tells you actually get closer to the critical point. And so the region where the intersection sits is the critical coupling. And then you can extract critical exponents in a way which is too long to fit on the slide, unfortunately. But the idea is that actually you can start from a lattice which is only 32 squared, repeatedly do this inverse renormalization group stepping. So you go from 32 to 64, 128, etc. And by comparing the configurations on different lattice sizes, you can extract the critical exponents. once you have this whole sequence, you can compare 32 with 256, but also 64 with 256, or 128 with 256. So you have a lot of comparisons to make, and ultimately this will converge to the expected, to the values of the critical exponent in the infinite volume limit. And this is the same. This is 5 to the 4, and so we expect this to be 7/8, and this to be 1/8. And as you see, it does converge there ultimately with some error here. So this is a kind of completely new way to think about renormalization group and a way to extract critical exponents, which is essentially fairly cheap, because you only need to do one simulation, say on 32 squared, and everything else is generated by these RG steps.
There's some correlations in that table, right? It's generated from the same network. Is that? I mean, those error bars are very suspiciously lined up, aren't they?
Yeah. So they definitely compute from the same network, but they also all originate from the same mother ensemble, say,
right.
which is at L equals 32.
Yeah.
So all these data are highly correlated. All these, yeah. I thought when you said there's correlation in the data, actually, there should be some correlation, some finite correlation length in the original configuration, because you're relying on the fact that these correlations are there. So once you scale them up, they get enhanced. If you would start completely in the broken phase or completely in the symmetric phase without any correlations, except that everything is aligned, say, you wouldn't be able to do this. You need to have some correlations which are then enhanced by this inverse combination. So this flows towards the critical point without critical slowing down. You can reach large lattices. Interestingly, the reason, so it had been done for the Ising model by Swansea et al. But what you do need is a reliable blocking step. So even the first step, the standard renormalization group step, has to be done. And here, actually, we propose a majority rule, which I think is new, but which was tested under the standard RG analysis, that it does converge to the expected answer. So this is a non-trivial element here. And the reason, for instance, we haven't done this for gauge theories, is that we don't have a reliable blocking step for gauge theories, say, to start with. So this only works when you have an implementation of the standard RG in one direction, because then you can invert. Just as a side remark here. Okay, I'll pause again. So in the last 15 minutes, then I'll talk about something which is even more speculative, but therefore interesting. I would think a lot of work has to be done still. This is one paper, and generally it opens up more questions than it answers. Is my experience giving this talk a few times. But I think the idea is quite clear. So this, now we are in the and back section. So machine learning for lattice field theories and back. So now we want to see what lattice field theory can offer to machine learning, and whether there are kind of synergies between both that can help us, for instance, to design machine learning algorithms, because we know very well how lattice field theories work, and so maybe that is beneficial for this area. And so the idea is really to say, can we derive machine learning algorithms from discretized Euclidean field theories? And the thinking goes as follows. A 5 to the 4th theory, again, just 5 to the 4th theory, is actually in the computer science literature, say, or in the mathematics literature, can be called a Markov random field. And this is due to a theorem. And a Markov random field is actually a known concept in machine learning. So Markov random fields can be used for machine learning algorithms. And so we want, well, I'll show this theorem very quickly, but then we want to say, can we now use 5 to the 4th theory to come up with machine learning algorithms which maybe the machine learning community would not naturally come up with, because they, we think we have experience with thinking about 5 to the 4th theory from, say, the lattice perspective. So this is all really not necessary, but so there's a graph here, and there are lines and edges, and this is a bipartite graph. This we'll use later when we talk about restricted Boltzmann machines as a hidden layer and a visible layer. and here the nodes in the visible layer don't talk to each other, do not talk to each other, but it is kind of not essential at the moment. I think the point is that the Hammersley-Clifford theorem says that if you have essentially a partition function where the Boltzmann weight, let's call it Boltzmann weight, can be factorized as a product of Boltzmann weights over what's called cliques, or over maximum cliques, then your field or your theory satisfies this theorem and is a local Markov field. This sounds a little bit mysterious, but the whole point is that our standard path integral, Euclidean path integral, with a Boltzmann weight e to the minus s, and with only nearest neighbor interaction, so the kinetic term is discretized, it's nearest neighbor interaction, and then you have local terms for a mass and a phi to the 4 coupling, that I can factorize the Boltzmann weight as a product of these size functions here. Essentially because I always say I have the local terms are easy, of course, and the bilocal terms involve, say, only phi 1 and phi 3. And so phi 1 and phi 3 actually form a maximum clique. In addition, phi 1 and phi 2 form a maximum clique. And so all these bilinear terms here only appear exactly once, and this factorization works, say. So it's a theorem, so it's rigorous. So with hand-wavingly, the Boltzmann weight can be written as a product of weights which only involve local terms and nearest neighbor terms in this case. And so the outcome of this discussion is then that the phi to the 4 theory on a square lattice is indeed a Markov random field. Now, in order to make this useful for machine learning, we have to be a little bit more general. Of course, if we do a normal phi to the 4 theory, we have one coupling constant here, lambda, which is the same for all lattice sides, and the same, say, with the mass term here, m squared, or mu squared, which would be the same at all sides. And the same for the hopping term, this would usually be called kappa and would be the same. And now in the context of machine learning, we want to be a little bit more free or unrestricted. So these parameters here, W, A, and B, are now made to depend locally on where you are on the lattice, say. And the reason we do this is that then we have more freedom to mimic probability distributions. So it increases what is known as the expressivity. We can express more complicated functions. And so a machine learning job is basically tune these coupling constants, omega, A, and B, collectively known as theta, tune these parameters so that you can optimize some kind of minimization procedure. Now, it's a slightly funny theory from a Euclidean field theory perspective, because it's not obvious whether you can take a continuum limit or a relativistically invariant limit, or even stability is not clear, because phi to the 4 coupling would swap signs, say, from one lattice side to the other. But some work has been done actually to look at quantum field theories where the couplings are local in disordered systems, for instance, or spin glasses are areas where you encounter this kind of setup. So what do we do in practice with this? So we now have we want to complete a machine learning task. So part of entering machine learning is that you have to learn the language that they use. So we want to do a learning problem and complete a task. This is what it's called. Our field variables phi here are essentially the degrees of freedom, and the action or the distribution contains parameters which have to be tuned. And the tuning is done by making sure that this distribution satisfies some specific condition which we put on. Now, there are two kind of standard ways to look at this distribution P. So we want to optimize this distribution P to some condition. And this means we want to learn what's called a target distribution. So Q is the distribution we want to mimic, and we want to find the parameters in P to do this, to mimic this. Now, there are two possibilities here. Either this target distribution is known, and then we just want to make P essentially equal to Q by tuning the parameters. you may want to do this if it turns out that it's very hard to generate data numerically from Q, but maybe this new distribution function is easier to use in sampling, say. So that might be the motivation to do this. In this case, we would have to know the target distribution, analytically. The other option is that we actually do not know the target distribution, but we have a lot of data available. And then we want to construct this P distribution to say, okay, this is kind of the distribution from which all this data could have been generated. And this is something that is very common on the kind of social media or other internet applications. And we do not know the distribution that determines faces or music or anything. But if you create this new distribution P, you can then use this to create artificial images or artificial music, or paintings in the style of Pollock or music in the style of the Beatles, by creating this distribution. So this relies on having a lot of data available, and then constructing the distribution which is tuned so that it reproduces that type of data. So how do you compare distribution functions? So suppose we know the target distribution Q, and we now want to find which distribution P mimics this distribution Q by tuning the parameters. And so the common measure that is used here is something called the Kullback-Leibler divergence. It's a distance between two probability distributions. It's given here. It's clearly if P is equal to Q, it's 0. So this is minimized when the two distributions are equal. And when P is not equal to Q, you can show that it's a positive that is larger than 0. So this is a measure on space of distribution functions, say probability distributions, which has to be minimized. And so that's the process. You want to minimize this by tuning the parameters here, and then sampling configuration from P. It sounds a little bit mysterious, but actually it's almost like a variational calculation. So it's something you may have, you're not that familiar with, but it's as I said. So if our Q distribution can be written as an exponential, and we have a free energy, and so this is a target distribution, and the distribution we want to compute can also be written as an exponential, and also there's a free energy, then this KL divergence essentially gives you this inequality. Namely, the target free energy is bounded by this free energy on the right, which only depends on the quantities of the P distribution. So if you think about it as a variational calculation, we want to find the distribution P such that the right-hand side is minimized, and that will provide then an upper bound to the real system. And you can do this by the way you do a variational problem. You minimize with respect to the parameters, and these are called theta, and so the minimization is just a gradient descent. So the theta, if you think about this as a wave function, a variational wave function with a few parameters, here we have a variational probability distribution with a few parameters. I want to minimize that. So in the machine learning literature, this is called gradient descent, and the parameter in front is called the learning rate. But we would just call it a step size or something like this. So let me skip ahead. So we have a target distribution, which is kind of funny. It has nearest neighbor interactions. It has next to nearest neighbor interactions. It even has a complex term in there. So it's a bit of a weird action. And we try to mimic this action using the one I introduced before, the 5 to the 4th theory, but with local couplings. And this works. So this is just to ensure this plot is not very clear, but it's to show that if we just have the standard 5 to the 4th theory with constant couplings, and we go through this gradient descent, that indeed the target distribution converges to the original distribution. So this is just a sign of stability, say. If you want to mimic something that is exactly encodable in this action, then that's possible. Here's an example where we have next to nearest neighbor terms in the target action, which we do not have in the P distribution. But in the P distribution, on the other hand, we have non-local terms, inhomogeneous terms. And well, this is showing that indeed the cobalt light divergence will go to 0. So we were capable of reproducing a target action with next to nearest neighbor terms. And then just want to go quite quickly. And then we can do reweighting as well in this complex coupling constant, both from the original theory as always, but also from this new theory P. So we can use this new probability distribution now to reweight in a parameter and get agreement with what you can do. So we can really use it. I'm rushing a little bit through here, I realize, mostly because I want to talk about the bird. So here we have the opposite problem. Here we just have an ensemble of birds, in this case, just one picture of a bird. And we want to tune the couplings in the 5⁴ theory such that it produces the bird. And this means we have to minimize this Kohlberg-Lightbot divergence where we have data. So previously I had P here, now I have Q here. So this is an average over data. But this procedure it chooses the coupling constant in the 5⁴ theory to reproduce this bird as a minimization problem. So this is about generating fake images, but I think it's amusing because this is a 5⁴ theory here with very, very peculiar couplings, which is obviously very far from the Higgs boson. And then finally, we can expand on this and put it in a neural network, so with more layers. So this is a bipartite graph, which is called a restricted Boltzmann machine. And here we've already now encountered a new type of system. So these machines have been studied quite a lot for Gaussian fields, for discrete fields, so for Ising model type fields, but not with 5⁴ interaction. So this is something that we're currently working on to see if a 5⁴ restricted Boltzmann machine would be able to yield more interesting things than a Gaussian or an Ising model restricted Boltzmann machine. So the last bit was rushing a little bit, mostly actually because a lot of work still needs to be done. So the idea is let's use lattice field theory lattice field theory language and lattice field theory setup to think about machine learning. Essentially, the neurons on the nodes are replaced by scalar fields. The weights and the biases living there are replaced by coupling constants in the field theory. And can we use this to come up with machine learning algorithms that are new and interesting, say? It's an unusual field theory because it's inhomogeneous couplings, but it's an interesting, new idea to work on. So as I said, it's relatively new field, I would say. There's a lot of things can be done. Phase transitions are pretty much, studied, so anything goes has already finished there. But in the last two topics I discussed, it's still much more free. So we're not going towards lattice QCD yet, but other groups are, especially the MIT group is doing something completely different with machine learning, but they are working on lattice QCD. So there's a lot of, prospects in that area as well. Okay, thanks.
Thanks very much, Gert. Are there some questions? So I'm just, your bird picture, just not sure I understand that quite right. So you start off obviously with a distribution that's basically a sort of delta function. It's a single image. And now what, on the right-hand side, you got the picture of the bird back again, but now is that, have you integrated over the variables there? Are they averages of in this model?
They're average, yeah. So you do it a number of times, even though it's only one picture on the left, you do an ensemble and you do it many times. It is a random process, so you get an approximate bird coming out, yeah. So
you average over each pixel and then you get the bird shape, and it's all just from a local interaction, but one that's inhomogeneous, so it's different coupling constants at different sides. Yeah, exactly, yeah. It's funny because exactly the same question was asked a few weeks ago when we were actually visiting MIT. So you could, of course, tune the couplings exactly. You could just have a local field and turn it on and off to some extent.
But the point here, I think, is that, we want to reproduce this picture using a 5 to the 4th.
So your constraint is that you've kept, nearest neighbor interactions in a 5 to the 4th. You haven't. I mean, you can obviously just select, define your distribution to be delta functions.
Exactly. But that would be.
I mean, that's a trivial solution.
Exactly. So the game was not to reproduce the picture any way possible.
Yeah.
The game was to use the 5 to the 4th theory, and then
and see how close you could get it. Right. I understand. Yeah. Okay. Oh, very nice. Yeah. Interesting. Very interesting.
Yeah.
And are the couplings? I mean, do they vary wildly, or are they? What's the biggest and smallest values? I mean, are they?
Yeah. So that's something we're working on currently, actually, with a master's student, to look much more in detail on what's going on, because we haven't looked at that, say, but from the field theory perspective, we want to know indeed what are the couplings, are the 5 to the 4, the lambdas all positive, so to say, because otherwise it will be unstable.
Right.
Vary during the learning stage. Just all these questions are there, but we haven't looked at them properly yet.
Yeah, very nice. Lucius has got a question. You want to go ahead there, Lucius?
Yeah, regarding the transfer learning thing again. So if I'm getting you right, currently you train at some value of beta, say, and then to get the machine learning to tell you something at other values at beta, you do this reweighting kind of using the outputs the network gives you. Has anyone tried getting the network to learn the more general pattern of, like, instead of giving it sort of the configuration, you give it the configuration and the beta and let it figure out from there what to do? Like, give it the beta as an extra parameter, and instead of learning how to classify at any particular beta, it tries to learn how to do it for a general range of betas. Have it do the reweighting itself, basically.
So you give it configurations at different beta values at the same time?
Yeah, that would be ideal. Like in training, you wouldn't give it configurations at just one beta. You would vary between a bunch, and you would leave the beta as a parameter that you actually tell the network even about, maybe. And then you hope.
I think that should be possible in a way, because
I mean, it seems like it should be possible if this reweighting is possible, because, like, if we can do a mathematical operation, probably some neural network setup can, but which one? Like, how would you tell this to a convolutional neural network, for example? How do we put the beta as an additional input channel, kind of?
Yeah, well, you can use it as a label, as an additional label then. But I'm thinking about this plot here in a way that this is at fixed values of beta, so to say. So this is in the ordered phase, and this is in the disordered phase. So if you put a configuration through here, the distribution of these weights would tell you not only which phase you are, but also what approximate value of beta you are, say.
Yes.
So as a, yeah. So you could have a third label, which is beta. It's like a continuous, well, you could have this one output label, which is beta, and then see if it can extrapolate. Yeah. I don't know, I obviously, we haven't done it. No. There is this idea, actually, that works very well with restricted Boltzmann machine, I think, where you know the Hamiltonian, and you have a whole set of configurations, and then you find out what the, no, sorry, you don't know the, don't know the Hamiltonian, that's the point. You want to learn the Hamiltonian. So you want to find out what the coupling constants are that would give rise to those configurations. That is a quite common, actually. So Luigi D'Ardebino and co-workers had a paper on that 2 years ago. So, and it's a common, it's a dog. It's a dog. Yeah. Yeah, so you can revert the problem. You can say, I have a set of configurations. I have a kind of model Hamiltonian with parameters, and I want to learn what the parameters are. Yeah.
Okay, thank you.
Gert is getting questions from his pets, but are there any other questions from the audience? We're a little bit over time, so perhaps if there's any last questions, now is your chance. No. Oh, no, I'm not seeing any more questions. Okay. Well, let's thank Gert again for a very interesting, illuminating talk. That was very nice. And I'll say good night, everybody. Thank you very much.
Yeah, thank you. See you. Bye.
Bye now. Bye.
Bye.
Bye.